Okay, so today we reach probably one of the most important lessons in our course, maybe even the most important one. The good news is not one of the more difficult ones. In fact, probably it's one of the easier lessons, but it's extremely important because we need to understand what constitutes a linear ordinary differential equation. Pretty much the entire course, and I think I mentioned this last time, is structured to developing a theory of solutions of linear differential equations or systems of linear differential equations, because there is a complete theory on how to solve these equations. So you need to, of course, first recognize what a linear ODE looks like. It's not a difficult concept. It's many people actually know what linear equations mean in general. We just need to know what that means, again, in the context of linear differential equations. So just to review from algebra, if I have just algebraic equations, so forget about for a moment about the differential equations. Just think about any regular equation from algebra when you just want to find an unknown, right? So for example, x plus 2 equals 5, find x. Or let's say x squared minus x plus 5 is 0, what is x equal to? Or let's say you have systems of algebraic equations. Let's say x minus y equals 2, x squared plus y equals 5. I'm just making up basically here various examples to illustrate that the concept of linearity is probably known to you from algebra. So once again, forget about differential equations for a moment. Think about just algebra equations. If I ask you which of these equations or systems are linear, I'm pretty sure you can tell immediately. The first one obviously is linear if you look at the variable x, right? I mean, it's in a summation with power 1. The second equation is not linear. The dead giveaway, of course, is x squared, because not linear means with the power 1, x squared makes it not linear. This one, as a system, the first equation is linear, but the second one is not because of x squared. So as a system, this is not linear. So it's not a linear system. And obviously this one is also linear. I mean, it's linear as the first two equations. So the first thing to keep in mind is that when we talk about systems, we want both equations to be linear, to call it a linear system. If you have a single ODE, a single equation, obviously you have to look at the variables to see if it's linear or not. So in other words, linear means that in the unknowns that you have to find in an algebra equation, these unknowns have to be at power 1 in a summation, and they may have, of course, constant coefficients, right? So I mean, you could have constants multiplied by x, for example, 7x plus 6 equals 9. That's also a linear equation. The important thing is that x should be by itself in a summation. And of course, linearity excludes any special functions. So for example, if you have sine of x equals 7, this is also not linear. We do not allow any special functions, just a linear combination in the variables. So pause for a moment and make sure you understand what that means in the context, again, of algebra, what a linear equation means. So once that is established, I mean, once that's clear in your mind, let's actually come up with the definition of what constitutes a linear differential equation. So in short, before I write the definition, linearity for differential equations refers to the linearity in the dependent variables and its derivatives. So remember, when you have a differential equation, you talk about y of t, right? I mean, you're trying to find a function of t. T, the variable of that function, has no restrictions. Linearity refers only to the dependent variable y. So let's write this as a remark. A linear ODE refers to linearity in y, y prime, y double prime, and so on, depending, of course, on the order of the ODE. So we want linearity in the dependent variable and its derivatives. T has no restriction. That's one of the first things to keep in mind, and that's one of the sources of misunderstandings in the beginning. So as a definition, the general notation or the general form of a linear ODE of order n looks like this. So a linear combination in the derivatives. So let's say a n of t, which is basically a function of t, times the nth derivative of n. This is a symbolic power, right? I mean, this isn't y to the power n. This is a shortcut notation for the nth derivative. So let's write it here that y n in the parentheses means the nth derivative of y. And then another combination like this, right? So then you may have another function of t and then n minus 1th derivative, and you keep on going until you have a 1 of t times y prime, maybe some function of t times y, and then maybe a term by itself with now a y, right, just a function of t, which you can write it on the right hand side. So this is like the standard form of a linear ODE. Of course, you can move the terms from left to right. It doesn't have to be arranged this way, but in order to organize our ideas better, this is essentially the way you write a linear ODE in the standard form. So you collect all the terms in y and its derivatives on one side of the equation, and then if you have another term that depends on t, you leave that to the right hand side. So again, the important thing to keep in mind is that there is absolutely no restriction on t. The only thing that makes it linear is the fact that the y's and its derivatives are in this linear combination. So of course, when we go over some examples, this hopefully will be much clearer to you. So let's actually write down a bunch of examples of differential equations in which some of them are linear, some of them are not. So for example, you could have cosine of t times y double prime minus t squared times y equals sine of t. And I'm going to get back to this, and of course I'm going to give you the answer whether it's linear or not. But while I move on with some other examples, try to anticipate the answer. Maybe pause again if you need to, and think about whether this is linear according to my definition. So do this. It's very important to try your best to figure out the answer before I actually state it in the lecture here. Here's another one. Let's say y double prime plus 5y prime plus 7y equals 0. Let's have y squared times t plus y prime times cosine of t equals t. Let's put another one, y times y prime plus y double prime equals t times y. And here's another one, t to the power 3 times y double prime plus t times y prime plus 7 times y equals 0. I think that's enough for now. Again, pause for a moment and try to figure out the answer. Question is, which of these is linear, which one is not? So again, try to match this with the definition. This is obviously linear. Well, maybe not obviously in the beginning, but it will be obvious pretty soon, right? Focus on the dependent variables. They are in a linear combination, right? They look like this. Doesn't matter if the coefficients depend on t. Doesn't matter if these coefficients that depend on t are not linear. So here I can have t squared cosine of t. The coefficients that depend on t don't have to be linear. So linearity again only refers to linearity in the y double prime, and so on. And of course here you have a term that doesn't depend on y, which again we can put it to the right hand side. This is again linear, the second one. Notice that the coefficients don't have to depend on t, right? You could have constant coefficients, and in fact that makes of course the equation easier to solve. This is one of the first equations we're going to learn to solve, in fact, in chapter 4 of the textbook, right, when we study second order linear ODEs. So linear, right? There's no term that doesn't depend on t on the right hand side, so that right hand side is 0, so f of t could be 0. And then like I said, all other coefficients are constants. This is not linear. The third one that I put here, it's not linear because of y squared. Okay, so it's not linear in y, therefore the entire ODE is not linear. This one is not linear also, because you have y times y prime. So the y and y prime do not appear in a linear combination. They have to be by themselves in these summations, maybe times a function of t, but not together multiplied in the single term. Finally, the last one is also linear, right? These guys come up in linear combinations by themselves, so they match the definition of a linear ODE. So hopefully at this point you understand what a linear ODE is. Go over the homework, and you have a bunch of problems when you have to recognize just that. Before we actually talk about how we solve them, there is another type of equation which we need to define, because that type is important when we build the method of solutions of solving these differential equations. So before I do that, let me actually go over just one another notation. The entire left side of this ODE sometimes is denoted by L of y. So I mean, if in order to refer to a linear ODE, and you don't want to write too many terms, this entire linear combination in y can be denoted by L of y. This is also called a linear operator. So when I describe, for example, how I solve a linear ODE, I may just write L of y equals f of t, just to denote a generic ODE. And by L of y, I mean just the entire linear combination in y, y double prime, y prime, and so on. Another very important definition: if f of t is 0, then the ODE is called homogeneous. That's another important term, because again, you will see the way to solve these differential equations is to actually deal with the homogeneous part of the equation first. You will see actually in today's lecture this concept. So, for example, if I look at this last, or the second, yes, and this one, these are examples of homogeneous ODEs. Linear, but also homogeneous, because f of t is equal to 0. So there is no non-zero term that doesn't depend on y. This is not, this is, for example, linear, right? The first one is linear, but not homogeneous. We're going to put more examples till the end of the lecture as well. But this is linear, not homogeneous, because you have sine of t. The second one is also homogeneous, because you have 0 on the right hand side. So before we move on to the second part, again, make sure you understand what the linear ODE means, how you recognize it, what the homogeneous linear ODE looks like, and then we're going to deal with some other examples in the second part.